All right. So got this book here, Mrs. Contreras. Geek Wisdom.
Ooh.
And in honor of the newest episode of The Mandalorian coming out, we're going to celebrate some Star Wars today. And I found in my Geek Wisdom book a quote from Yoda. So anyone out there who doesn't like Star Wars, you're wrong. But also, even if you don't like Star Wars, I think there's a lot you can learn from certain characters in Star Wars. This one's from Yoda, small little green creature from, how do you pronounce it? Dagobah?
Well, I don't think he's from Dagobah. He went to
know,
exile himself to Dagobah, but that's part of the Mandalorian. It's like learning about the species. Yeah. Yoda and Yaddle. There's like a female of the same species who's also on the Jedi Council.
Mm-hmm.
But she's like 300 years younger than Yoda, who's like 900 or something.
That's right. All right, here's the quote, though. I think it's something that we could take into the next few weeks. Try not. Do or do not. There is no try.
So are we going to try to do this worksheet, Mr. Kirk?
No, we're going to do it.
We're going to do it.
We're going to do it. And maybe we'll fail along the way. You know, the more I think about this quote, I'm like, that's not that good of a quote. I think it's okay to try.
It's okay to try, I think. But the other one that he says of the failure is the best teacher. No. The greatest teacher, failure is. What is it?
You got to do it in the backwards way.
The greatest teacher, failure is.
I feel like that quote and the quote I just read kind of contradict a little bit.
Well, maybe it's Yoda having a growth mindset.
Yeah. Maybe. Or maybe it's just when he says try not, do or do not, he's just trying to tell us to like jump in and do it. So let's do that. Let's jump in, and you know what?
You need to share your screen. You can't jump.
I'm gonna try to like sync this up. Ready? It didn't work.
It didn't work.
There we go. Sweet.
Nice.
All right, so we're graphing higher order polynomials. Higher order just means that power is larger than 2. But we're gonna start with some 2s.
You're kind of muffled. Did something happen?
I sound muffled now.
Oh, it's better now.
It's better now. Okay. Cool. All right, so let's give our page our header. So boom, the date is today. The period is a positive integer. I guess I could have done natural number like I've done in the past. All right, so graph the function below. How have we done this in the past?
We have we've completed the square and found the graded and find the vertex form.
Let's do it. Oh, you Yoda'd me while you were talking to me. That's a pretty good Yoda.
Thanks.
All right. It needs like a little like smile. It just looks stressed. Anyways, let's complete the square. We got -8 divided by 2 squared is 16. -8 divided by 2, -4 squared, positive 16. So I'm going to take a page from your book and just add 4 or subtract 4. X.
Because 12 plus 4 is 16. That's way easier. I don't know. I think.
I agree. When the fractions get in there, I want to like know this other technique. That's kind of my pedagogical reason for doing what I do.
And that makes sense.
For students, for those who don't know, pedagogical just means the way a teacher teaches something. And if it's a good way to teach it or a bad way to teach it. In a nutshell. All right, we got x minus 4, quantity squared, minus 4. Boom. Let's graph this thing.
Got the vertex, and then we just parent function.
Want to graph it for me?
I guess so. So we have what?
Like, you gave me the boring part.
-4. Did I do that point right?
Yep.
And then we got just like, we just do this in our sleep. 1, 2, 3.
Boom, boom, boom. Ba-da-da-da-boom.
And whoop.
Are you about to graph drop? Graph drop.
Boom.
All right, sweet. We got that. That wasn't that bad.
Yeah, because you made me do it.
If I did it, it would have been awful. All right, let's keep going. Let's see what else this lesson here has in store. Alternate method.
Hmm.
Do you think it's annoying that I pretend like I don't know what's coming?
No, I think it's endearing.
Alternate method? What could that be?
Well, in our last video with optimization, we leveraged another form in order to find our mins or our maxes, depending on what the question was asking us. So maybe
leverage form we did.
Leverage.
Should we try to Yoda as many sentences as possible? I've been told no from my producer.
Very annoyed the students will be.
Very annoyed the students will be.
Perhaps a goal of that it is.
We'll squeeze in some Yoda when it's not actual math time. All right, so all the factored form. Had you said that?
Yeah.
Okay. My short-term memory was.
Form, we can do.
Are you ready?
No, I'm about to Yoda you.
Oh, I caught you red-handed. Yoda green-handed.
Green-handed.
There's a difference between Yoda green and Kermit green. Let's just like make sure that we're all aware. Here's Kermit green in the corner of the screen. There's Yoda green right there.
Got it.
Anyways, I'm trying to factor this thing. Let's see, we got -6 and -2.
Yeah.
Boom, 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 boom. And then that tells us our roots. Do you want to graph this one? No,
I can graph
it. I'll graph it.
Okay.
1, 2, 3, 4, 5, 6. 1, 2. All right. What else can I graph?
You can graph the. Is it upward facing or downward facing?
This is upward facing.
Okay. And we can find our maxima or minimum, right? We can find a vertex.
Our optimization point.
Use the symmetry.
Symmetry, so that's going to be a 4, and then we just need to know the y value at 4. So like right quick, 4 minus 6 is -2. 4 minus 2 is 2. That's -4.
Boom.
And then it agrees with how we graph things very quickly. Over 1 up 1, over 2 up 4, etc. I could have gone down over 2 down 4, I think is another way to have thought about this.
Mm-hmm.
Or you just green crabbed me. No one wants a green crab.
Why?
2, 3, 4, 5, 6, 7.
It's just covered with algae.
Symmetry. Did you say algae? Is that actually how you pronounce it?
No. Although algal blooms, I think that's something that's it's a major problem.
Let's get Ms. Duval on this this math lesson podcast thing that we do.
Yeah. Maybe
Ms. Duval is the one of the marine. She is the marine biology teacher, but also you learn about marine biology in biology. She's also a sophomore biology teacher.
And she's the ento teacher, entomology.
She, I'm sure, has a lot of work to do with that many preps.
Yeah, that's a lot of classes to teach.
She's awesome. She's an all-star. She can handle it. All right, we got the graph. And I would argue that might have been faster. Of course, we took about the same amount of time, but boom, boom, boom. Like, I guess, objectively, this was 2 lines and this was 1 line.
Yeah, that's true.
So, alternate method, not better.
But we did the symmetry part in our heads, right?
Yeah, and I don't know if you noticed, but when you're talking about algae blooms, what did you say?
Algal blooms.
Algal blooms. I had gotten my symmetry point over here. I didn't do all the counting or plugging in. I just boom, boom.
You just clicked.
Cool. All right. So this lesson, now that we've kind of warmed ourselves up. I just cracked my back. This lesson is all about graphing polynomials. We've just graphed quadratics. And this second method made it kind of nice. We were able to graph the roots. So let me go ahead and scroll down, see what else this lesson has in store. Graphing higher order polynomials. And I have given it to you now in factored form. So crossing fingers, we know what to do. What are you thinking?
Plot our roots.
Plot our roots. So got a lot of space here. We can talk about a lot of things. But what are our roots?
0 and anything that makes anything our parentheses 0.
Are you cool if I use this symbol for my roots? R sub 1.
Yeah, I think we actually used that without talking about it in our other video with yeah. But yeah, R sub 1. That's that's how we talk about like subscripts are a way of using the same variable, but like again. And you might have seen it in talking about like the slope formula, y2 minus y1 over x2 minus x1. That's this is another way we can use subscripts, and it also comes up a lot in any summation things.
Summation. And we've used this symbol before. Some of you have written about it in your journals.
Sigma.
Summation. Sigma notation. Sigma notation. Oh, this is totally where our faces are.
Yes.
Zoop, I wrote sigma notation. There's also another symbol that might come up in a second. It's not. I just wrote a pi symbol, and I want to make sure everyone realizes that I'm drawing a capital pi.
Capital pi. Not to be confused with lowercase pi, which has a little bit more curly stuff.
This is a product. P product. Sigma summation. All right, back down to where we were though. We got root sub 1 is 0. Root sub 2 you said was
-5.
And then the third root we've been given is
-3.
-3. Cool.
Does it matter what order they're in?
I don't think so, right? Because we are defining variables here.
Right.
Now, so I'm going to go ahead and plot these things. 0. When I plug in things into this function, I'm going to get a value. But I know that when I plug in 0, -5, and -3, I'm going to get 0. That's what a root means. That's one way of thinking about a root. All right, so we're kind of like getting this graph. What is the largest power?
The largest power, or the degree of our polynomial, is 3.
/ degree of polynomial is 3. If I expand this, I'm not going to worry necessarily about expanding everything. But if I expand it, just those x terms, my first one's going to be an x to the 3. Let me actually write this. What is the first term? Can you just get the first term kind of willy-nilly?
Yeah, it's -1.
And I'm going to write leading term because first term is kind of ambiguous. Depends on how you write it. Leading term referring to the term with the largest power. So you said x to the 3.
With a -1 as a coefficient.
With a -1 as a coefficient. So boom, 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 expanding, we get a negative cubic.
Negative cubic. Which way does that go?
That's
Wait, my camera. I don't know which
I don't know if I'm being flip-flopped. I think this is what it's gonna be. You're doing it right from my perspective. So hopefully if we both do it, then one of us will be right.
Wait, no, but then we matched. All right, whatever.
Anyways. All right, so this is gonna behave that way. It's gonna be like a negative cubic. So it's gonna start up here. It's gonna go down. It's gonna go through. And then a -3 it's gonna go through. And then a -5 is gonna go through. Boom. I want to verify that this actually happens. When I plug in like the biggest number possible that I know.
7.
Am I getting 7 is humongous. If I plug in 7, I'm going to get 10 times 12, 120 times 7, which is 120 times 7 is 7 times 12 is 96? Or is it 72? 72?
96. No.
720. Negative 720, right? 7 times 12. 8 times 12 is 84.
8 times 12 is not 84. 8 times 12 is...
Didn't you say 12 times 6 is...
12 times 5 is 60.
Wait, so what is it?
12 times 7 is 84.
84. So 840, negative 840. I'm getting at 1, 2, 3, 4, 5, 6, 7. I'm way down at 7, negative 840. All right, so it is shooting down. Likewise, if I plug in the biggest like negative number right now, negative 7.
Okay.
I'm not going to do the math, but I should be getting something super positive.
That's actually easier.
Yeah, it is actually. Negative 7 plus 3 is negative 4.
4.
Negative 7 plus 5 is negative 2. That's 8. And 8 times positive 7 is 56. 56. So I'm getting, so at 5, 6, 7, I should be at 56. Boom. All right, so this is doing the right thing. So what are some conclusions that we can make about higher degree polynomials?
Well, the roots are very helpful in like making our graph, if the goal is graphing. Put the roots in. We might have a little bit of trouble with different degrees though, because with like the third degree polynomial, if we have 3 roots, then like everything is pretty straightforward. We just go through each of the roots. But there might be a little bit of tricky things happening once we have different multiplicities. But that's a problem for the next page and for future us.
I think the other thing I want to add is the end behavior of a polynomial is going to match the leading term's end behavior. So our leading term here is negative x cubed. Our function f of x, its end behavior is going to be the same as negative x cubed, because as you plug in larger and larger things, the only thing that matters is whatever term is largest. When you plug in negative 1,000,000, if I have x squared plus x, this x kind of means nothing when you plug in really large numbers. Negative 1,000,000 squared is going to be 12 zeros. Minus 1,000,000, still a massive number. Right? As numbers get larger, the whatever term is the largest power is going to dominate the rest of the polynomial. So our end behavior is going to match our leading term. Let's use that information for something that let's see what happens.
And just to backtrack again for that we have a odd leading, or we have an odd degree. So then our end behavior is in different directions. Whereas if we had an even degree of our polynomial, then we would have end behavior either both positive or both negative.
I don't have a ton of room, so I'm just going to write odd degree, different directions as it pertains to this problem. But yeah, you've said now that even, it's going to be the same. All right, boom. X squared minus 5x times x squared minus 4x minus 21.
Whew.
Let's draw a sketch of this thing.
Can we factor a little bit?
Let's do a little bit of factoring. So I see a GCF here. X times x minus 5. And then this one over here looks factorable.
Yeah, like negative x minus 7, x plus 3.
Negative 7 plus 3 is negative 4. And product negative 21. Beautiful. Our roots, let's just knock them out. Let's not take too much time on this one. 0.
5, 7, and negative 3.
Let's plot them. Okay. 0, 5, 7, negative 3. Cool. Largest power.
We have a degree 4.
And is it positive? I'm not looking right now.
Our leading term is positive, yes. So we have end behavior that is in the same direction because we have an even power and they're both going up.
I like to think of like x to the 4th as like a bodybuilder. Like.
Oh, okay, because there could be like different.
The muscles do this.
Oh. I was thinking the elbows. Like your shoulders are the roots, so then you could have it like this, or you could have it like this.
And if you like go low enough, your wrists would then be the other roots. We are not funny. We are not funny.
I think we are.
Oh, I call this the Wumbo graph.
The Wumbo graph?
Yeah. Like a mix of W.
What's Wumbo, though?
Wumbo is like, it's the opposite of mini.
Okay.
Yeah. It's like, if you have mini, it's an M. If you flip it upside down, it's a Wumbo.
Oh.
Yeah, that's a SpongeBob reference. I'm kind of disappointed in you.
Sorry. Didn't have cable growing up.
Neither did I. I had season 2 on DVD. Never saw season 1. Never saw any. It was a gift. All right. There is our graph, and we're done. I think if the goal is to just get a quick sketch, we're looking for a few things. Largest power. The positive or negative largest power. And then the roots. All right, let's complicate things a little bit more. Oh, did you draw an attempt at SpongeBob?
I did.
Nice.
pretty
I almost missed it. I almost missed it. All right, so we got things are changing up a little bit. A few more examples. We have negative x minus 3 quantity squared. I think we just know how to graph this.
Yeah, because it's just a parent function of x squared, and then it's shifted to the right, which I don't know which direction is right for you all. And then it's flipped upside down, reflected, because of the negative in the front. Yeah, so this is also like vertex form, right? When you have a plus 0. Nice.
Boom. So here we only have one root. Now I want to introduce something to kind of cover our bases for our future topic. But I actually like to consider that this function here has two roots. It has a root of 3 and 3. But that sounds stupid. 3 and 3. So what we actually say is 3 is a root with multiplicity 2. And you can imagine how a root might have multiplicity 3 or 4 or 5. With multiplicity 2. So whenever I give you something, whenever I give you a function with a power of 5 or a power of 7 or a power of 3, it's going to have 5, 7, or 3 roots respectively. We just double count sometimes. In this case, we're double counting. Is there anything else that we should add on this problem?
Well, we do want to note that what happens at that root is different from what happened before. Because what we have at this root is that the function is approaching the axis and then leaving, like going away from the axis. So there's like a
touch,
yeah. And
then a turn,
and then run away.
Ah.
So with our previous problem that we were graphing with our roots, we were going straight through the axis. And if you like zoom in on where those graphs were, we're pretty much having something like a line that's going through. Like if you think about like very, very close to those roots, what the function is going to look like, you could approximate it pretty well with a line.
I'm not going to zoom in any further, but yet there's a line going on there. Like one thing that we can do if we want to get real fancy, like imagine plugging in negative 3. Let me come back to this idea if I can generalize it a little bit more. But I don't want to start talking about something and then lose my footing. But there's a way that we can actually find out what line is happening here. But let's not worry about that right now.
Yeah, that's a calculus thing.
Yeah. When we have, not we, when we have multiplicity, of 2, the graph behaves like a parabola. The graph touches and then runs away.
That's our math terminology.
Right. It is tangent to the x-axis. Let's actually use some real.
Yeah,
that's
tangent.
A little bit more mathy. All right. So over here, do we have any roots that have multiplicity?
Yes, actually, we have it's like the same function happening twice, and then we just multiplied some more things onto it. It was like we're really efficient in our worksheet making.
Yeah. So the root 3 has multiplicity 2. I'm just going to write multi-dot 2. It has multiplicity 2. So at that point in this graph, we're going to touch, tangent, turn. TTT. We also have negative 5.
Negative 5 is a root, and it's like a regular root.
Yeah, we're passing through like a line instead of passing through like a parabola. And then similarly at 1. 1 What is our largest, what is our leading term?
Our leading term is negative x to the fourth. So we're going to have n behavior going down on both sides. A good bodybuilder flexing.
What's happening at 5 as I go?
You're just passing straight through.
Pass through.
And
What's
then
happening
at 1, also passing through. And then at 3, wait, what happened?
I deleted it because I was unhappy with my curve, but I realized that the whole thing disappears. All right, then what's happening at 3?
And then it's a tangent parabola.
Touch, tangent, turn.
Touch, tangent, turn.
I'm a fan of that. That is, I'm going to use that for now many years, I'm sure.
All right.
That's not true. I'm going to forget in the next 5 minutes.
Well, if we write it, touch.
Tangent. Wait, are you writing or am I writing?
I'm writing it.
Boom. Oh! Touch, tangent, turn. All right. How about a cubic? How about multiplicity 3?
Well, that's a parent function. We can handle that. It's just a cubic function, and it does go, and this was something that you harped on a lot for no apparent reason to our students, but you were seeing into the future, where we really wanted to make sure that when we're graphing cubic functions, we have something like a horizontal part of it.
So we leading power x cubed, it's going to start down here, end up here. And then as we approach,
flatten out.
Flatten out. Oh. This does have rotational symmetry, so hopefully my final answer will look mildly nice. Boom. All right, so when multiplicity 3, we touch, tangent, continue. I don't have a good 3 consonant. There's a term for it in literature. I forget what it is.
Alliteration?
Alliteration, yeah, thank you. I don't have 3 T's for this one. Multiplicity 3, we touch, we're tangent.
Touch, tangent, through?
Touch, tangent, through. All right, so over here, what's happening? At -4, touch, tangent, through. I got really loud there, sorry.
You did.
And then at 1.
Kind of peaked a little bit.
All right, so
tangent through.
What's the leading term in our second one over here?
It is a positive x to the 4th. So we have bodybuilder. I forget what the SpongeBob thing was, but what?
Wumbo.
Wumbo.
So we're starting x to the 4th, positive x to the 4th. We're starting up here. We're going through. But we're not. We are going through. But what's happening really close?
Touch, tangent, through.
Touch, tangent. We are flat, through. And then we're making our way back up. Making my way back. What's the lyric?
Making my way downtown.
Downtown.
I actually don't know the rest of it.
Full width. Let's just like confirm this with a graphing calculator so that we're not like incorrect. It's always nice to just double check yourself with the computer. We got x plus 4 cubed times x minus 1. X plus 4 cubed times x minus 1. Look at that.
There you go.
It goes way lower than
Whoa. Good thing we didn't have a scale on the y-axis.
If you've been wondering, students, why there's no scale on the y-axis, that is why. No pun intended. But look, if I zoom in, that is totally a touch, tangent, through. And that's just over here. That's just a line. That's just going through. No tangent. Touch through. We back. Cool. We graphing polynomials. This is good.
Guess we can generalize now then, huh?
Let's generalize it. All right, so we've been talking about these little different nuances in graphing polynomials with degree. Well, 2 worked, but in general, any degree polynomial. Here it is at the top. Hopefully that's not overwhelming. We got the function. Let me reattempt my underline. F of x equals a times x to the n plus b times x to the n minus 1 plus c times x to the n minus 2. All right, b, c, d, e, f, all of them could be 0. We could have a times x to the n, but we're ordering it with our polynomial with a largest degree at the front. If n is even and a is positive, what is this graph in general going to look like?
We're going to have n behavior that is going the same direction. They're both going up towards infinity.
And then who knows what's happening here?
Something.
Oh, you crabbed me. You crabbed me. All right, this is like a wumbo graph, but a little bit more.
Like a wumbo bumbo?
Wumbo bumbo. Jumbo. All right, plus x to the 2. I don't want to use n. M, where m is a natural number.
All right.
Not integer here, because if it's negative, then it's going to be doing lots of weird other stuff. We're looking at polynomials, not 1 over x graphs. Cool. All right, what about when n is even, but a is negative?
Then we're going to take that and we'll just reflect it down, because we got n behavior going in the same direction on either side. We have something crazy going on in the middle. Oh, that was extra crazy.
That's a wumbo, jumbo, lumbo, tumbo, gumbo. Shrimp.
Ooh, gumbo. Mm.
And as odd, a is positive?
Then we have, oh, shoot. It's going like this, I think, where we have, as x approaches positive infinity, our function's going up. And as x approaches negative infinity, our function's going down. Something crazy is going on in between.
What just happened?
Whoa. That's wild.
Boom. And then last but not least,
Switchy.
negative x to the 2m plus 1.
So our right end behavior is negative, left end behavior is positive. Like that. Nice.
I don't like how that looked. Psych.
It's a sketch. Okay. I like how you put the arrows in before you did everything else. I think that's helpful.
I think so too. I don't know. It's not something I necessarily say every time, but thanks for pointing that out. I appreciate the compliment.
Yeah, because it also it draws your attention to the end behavior, because that's the main point, right?
Mm-hmm. We care about 2 things: the roots and the end behavior, and everything else is just I don't know what the y value is. I know it's positive. All right. Speaking of which, we could use this to solve inequalities.
Whoa.
All right. Write a possible rule for the function graphed below. Now we're working backwards. We're given a graph. We want the rule. I think we've pretty much established what we need to get the graph, though, right?
Mm-hmm. Yeah.
What are the 2 things that we need?
The degree and the sign, I guess. The sign of our leading term.
Yeah. So let's just call it the degree and the coefficient.
Mm-hmm.
The sign of the coefficient. This is saying a possible rule. Let's underline that 5 times.
Ooh, possible. So we can just put in some numbers and it's okay.
Yeah. All right. So we need the degree, which is in this case, what's it going to be?
I think it's a 3, because we have going through all of our roots. It doesn't look like we have any with multiplicity other than 1.
Yeah. If I look over here on B, we have something going on there, but that's not happening over here.
Mm-hmm.
These are all going straight through. So it looks like degree 3. And then the end behavior tells us is this positive or negative?
I think it's positive, because when we're positive x values, our right end behavior is going up.
Cool.
Increasing.
And then there's one last thing I think we can do, right?
Yeah, we can just read off the roots and
roots.
then plug it into our factored form.
So I see there's no scale.
Yeah.
But let's
So
just pretend like the scale is 1.
Yeah. 1 is good.
-4. -1. 3. So what is a possible answer in red good terms?
Good terms. We have x plus 4 times x plus 1 times x minus 3 times some number. 1856.
Nope, too bad. Fine,
1856, come on. Go terms.
1856. Yeah, a lot of public universities started in the 1850s.
Yeah, because of the land grant? Morris land grant?
Yeah.
Something like that.
If anyone wants to write about education history in your journal, that could be a fun topic.
Mm-hmm. Or about how states got their shape. That's also interesting.
Oh, yeah. All right. Let's knock over. Let's go on over to B. There's a lot going on
change
here.
over to a history class right now. You want to All right. So we have it looks like an even degree because we have our end behavior going in the same direction. We have both of our end behaviors going up, so we know our leading coefficient is positive.
So before we said 3, I'm just going to put even right now because there's some weird stuff going on. We'll inspect that in a second. So degree even, you claim to be positive because it's going up. I'm on board with that. Roots.
So we have like a multiplicity of 2 going on
at 3.
3.
So R1 is equal. I'm going to say R1 is 3.
And then R2
with multiplicity 2.
2
or like an even number, right?
Some even number, yeah, that's true.
Right. Because let me jump back to Desmos real quick. Like x to the 2 touch tangent turn. But if I like throw an end there and then add a slider, well, that's kind of cool.
That is cool.
Even with the decimals, I don't want this to be. How do I?
Step is 1.
Step. I want it to be 1. Boom. Yeah. Now that the step is 1, terms. These are all even because of my 2n. So all of these are touch tangent turn. They're more sharp, but honestly, I don't think we can decide whether it's 2 or 4 or 6 or 8 just from this sketch.
Because it's the scale isn't really helpful.
I think a possible answer would be 2. So we'll put 2, but I don't want to say that it is 2. We don't know that for sure. What else do we got here?
2k instead.
Yeah, we could like give every possible answer. I like the idea of that. All right, what's another root?
0.
0, and that looks like it's just a line. So that's not going to have anything going on there. What's happening at 1, 2, 3, 4, 5? -5.
-5 looks like it has a odd multiplicity, but I guess we can't really say if it's going to be 3 or 5 or so 2. Oh, L. I see you.
2L plus 1. I don't want to use K because I'm not explicitly saying that they are 1 apart.
Correct.
R1 and R3. All right, so I think that we got something going on here. Even power. So our leading term needs to be positive. And then we have, I'm going to function notation over here. We got x plus 5 to the 2L plus 1 times, just x. That's nice. Times, I was worried about space, but I think I'm going to be fine. X coming in clutch. And then x minus 3 to the 2k. And then let's throw a number in front of here. Oh, since we're doing like any, let's do a.
Oh, yeah.
Right? Like we could put a 2, but I think that defeats the purpose of the L and the K.
We should also say what A, L, and K are elements of.
Yeah, A, L, and, well, A could be any number.
A is any real number.
These are natural numbers. We can't have negative numbers for those. And A is a real number. Good stuff. Yes. No, A is not a real number. A is a positive real number.
A is positive real.
Yeah.
Yep. Better stuff.
Boom. All right, we got one, I believe, two more, and we'll close this video out. Maybe we'll leave that one for the viewer. Let's do this one. Given f of 2 is equal to 0, sketch a graph of the function below. We are graphing higher order polynomials in this lesson. We have lots of tools under our belt.
So f of 2 equals 0. That feels like it's a clue.
Did you ever watch Blue's Clues?
Yeah, I did watch Blue's Clues very occasionally.
I thought was Blue Clues on cable?
It was. I watched it at my grandma's house.
You watched at your grandma's house? It was on Nick Jr.?
Maybe.
The producer saying Nick Jr.
Oh, okay.
That's what I'm going to refer to as Mary Kate now.
The producer?
that way I'm just not always referring to this like arbitrary name that, you know. All right, anyways. All right, so 2 is a root. Okay, cool.
Well, because didn't we talk about like roots were really helpful when we're looking at polynomials? Because we could get like a factored form by dividing our polynomial with polynomial long division. Although some students have journaled about liking synthetic division more. That's nice.
That's fine. That's fine. That's cool.
You do you.
All right, you're going to have a bad time when your root is like 2x minus 3. Can't do it with a leading coefficient of not 1. So that's why polynomial long division is useful. It's good for everything. Synthetic division requires a leading coefficient of 1. So that's kind of annoying. Those who don't know what synthetic division is yet, don't worry about it. You're not going to need it for the course right now. It will be taught in Precalc C when you're doing a lot of cool things with matrices and stuff like that. So let's continue. We got x 49x squared plus 129x minus 110. I guess I'll add one last thing is you're entitled to your own opinion. So if you like synthetic division, by all means, we're not going to stop you from doing something that you know. As long as it doesn't conflict with what our objective is. I could hear you like.
Sorry.
It's okay.
I tried to mute.
No,
and
I don't
didn't
care.
do it.
You're better than me because when you were talking earlier.
You got the clinking ice.
But it's a really good sound. All right.
Yeah, it's true.
We are subtracting out x minus 2, dividing out x minus 2. Let's do this thing. So we want to get an x cubed, so we need to multiply by some form of x squared.
So we need 6x squared,
6.
I think.
Boom, 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 boom. 6x cubed minus 12. What's going on, Pen? You're better than this.
Come on,
I'm going to go my parentheses for Mrs. Contreras.
Nice, thank you.
Boom. I need everyone to know that I use parentheses. I'm not a barbarian.
Okay, all right.
0, that's going to go away. I'm not going to cross anything off, though. Negative 49 plus 12 is negative 37, right?
7. Mm-hmm. Mm-hmm.
If you talk with your voice really high, it helps you with math. Bring the 129 down.
Is that a thing?
Yeah.
Come here,
watch.
29. Come here.
Watch. We need a negative 37x. So negative 37x squared.
Oh my gosh.
And then multiply. Get a plus 74. 129 minus 74. 26 to get me to 100. 29 to get me to 129. 26 and 29 is 35, 40, 45, 55.
Sounds good.
Cool. Bring the one. Oh, yeah. Oh, yeah. We've been given that f of 2 is a root. So we know we're going to get a remainder of 0. But it's still satisfying when you get it.
Very satisfying.
It's still satisfying when you get it. How do I get rid of this? Plus 55?
55.
Yep. Minus 110. Boom, 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 boom. Wait, what do we? Go Terps, go Terps, go Terps.
0.
That was the last video. 0. I like to put little
this is the
faces
Star
on
Wars
numbers.
one, so we should be doing like.
We're not doing enough. I'm mad at us. Anyways.
I think we've done a lot of it in previous videos, so it kind of like makes up for it. It's like aggregate, you know.
Yeah. All right. Let's get this thing. We got f of x. The fact that this this algebra has given us a remainder of 0 tells us that x minus the function can be factored to, not negative 2, x minus 2 times my quotient. And I think that thing is going to factor, because otherwise we've done a lot of work for nothing.
You can
All
feel
right.
it in your bones.
We got to factor this thing. I'm going to throw it over here for the sake of space. What does that thing factor to?
So 55 is what, like 5 times 11?
5 and 11, 11 and 5, 55 and 1. I always write it because you never know. I think that might be it, because 5 times 11 is prime.
So prime factorization.
Sweet. So then over here we have 1 and 6, 2 and 3. And we don't need a flippy floppy because we've already flippy floppied on the other side. Let's see if any of these give us negative 37. 11.
1, 6, 55s? No, it's too much. 2 3s, 55s.
Oh, wait, I think
11? Yeah.
I think I beat you. That's 22 and 15.
All right.
All right. So we have a 2 and a 5 and a 3 and an 11. These ones are going to get X's, and now we just need to figure out those signs.
I think we need negatives on both, because we have positive 55.
X minus 2 times.
I'm kind of upset that you didn't sing 22, because whenever I encounter 22, no, like 22.
Oh, like Taylor Swift, T-Swift.
You
know, one of my best friends, it has a very successful Taylor Swift fan Twitter.
What does that mean?
Like, he gets sent free stuff from Taylor Swift because he has a Twitter where he's like a fan and he tweets about all the Twitter stuff and the Taylor Swift stuff.
Wow. I didn't even know that was a thing.
Yeah.
Taylor Swift's cousin went to my high school, and her name is also Taylor Swift.
Really?
So Taylor Swift went to my high school, but not that Taylor Swift.
That's a shame.
It's okay.
Wait, the cousins are named the same?
Yeah.
Anyways, we got 2. We got 5 halves, which is 2.5. Okay, you mind if I change the scale?
What scale?
The scale of this graph.
Sure.
Because I don't... yeah, I'm going to change... I just don't want to be... You know what? I'm not changing the scale. Okay. We're zooming in. What are our roots? What would they say in Star Wars?
They don't really.
Light speed?
Or
is that stuff?
I don't know. I don't
Star
think
Trek says warp speed.
Warp speed, yeah. I mean, they talk about like jumps. I don't know. They don't have in my. I've been stumped. Maybe a student will know.
All right. All of these roots have multiplicity 1, right?
Mm-hmm.
Cool. All right. So 2, 2.5. This is why I'm zooming in.
Mm-hmm.
And then 11 thirds.
Which is
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 3 2/3. All right. Our leading coefficient was a 6, not a negative 6. So we're starting down here, ending up here.
Mm-hmm.
And all of these are multiplicity 1, so we're just flying through. Zoop. Zoom. This kind of curves up. It's not like a straight line there at the end, but it's a sketch. Let's zoom out, see what it looks like. Not bad.
Sure.
All right. Just like before we close this video out, because we're not going to do this one, what are your thoughts here?
Well, we're given that f of 1/2 equals 0 and f of 4 equals 0. So we're actually given roots, which is very helpful. We can use those to figure out maybe like a factored form of what our big long polynomial is using polynomial long division like we did before. But we also have, that would only give us 2 roots. No, we were given 2 roots, and then dividing out would give us maybe 2 roots, maybe 1.
With multiplicity?
With multiplicity of 2.
It will always add up to 4.
Correct.
Yeah. If you count the multiplicity as the multiplicity 2, 3, or 4, or 5, or 6. Yeah, there you go. Graph on higher order polynomials in a nutshell. We could do this for days.
We could. We could also not.
We can also not.
We could move on to other things.
Yes. How do you want to close this one out? It has to be Star Wars related.
Favorite droid.
Favorite droid? Are you gonna say BB-8?
Maybe.
She's a BB-8 right next to her. You know who's not? C-3PO.
C-3PO is not your favorite?
No. Oh, what was that? What was the droid in Mandalorian?
That
who
was
sacrificed
the nurse
themselves.
Nurse droid something. But
that one. That's my favorite droid. That droid was too legit to quit.
That was until he got blown up. But
yeah, he did quit. Yeah, right. But yeah, I'm gonna go with that one.
That's fair. Actually, I think I like K2SO from Rogue One. I think I like K2SO
Rogue
better.
One was phenomenal. Better than all 3 of the newest movies. Hands down. That movie was excellent.
I think
we can all agree that Solo was the worst.
Yeah, Solo was pretty bad.
I saw it on my birthday.
Oh, I'm sorry.
All right, let's close this one out.
All right. Wait.
All right, we're back. We forgot to say the most important thing in the world.
Live long and prosper.
Oh, no. Although Star Trek is pretty great. Live long and prosper, but also may the force be with you.
May the force be with you all.